So this next section, 6.5, is called Antiderivatives in the area under the curve. Now we did skip over section 6.4, which was called Riemann sums. And what Riemann sums look at kind of looks a little bit like this. Let me draw an analogy for a second here. So early in this course, we looked at tangents to a curve, and we looked at secants to a curve, and we looked at the slopes of these secants. And as we took this interval between 2 points that got closer and closer together, we took the limit as the distance between those 2 points became closer and closer together. And as that happened, we got closer and closer to creating a tangent line, which ended up providing us with the slope. As if we looked at the rise over the run, we came up with the tangent line by looking at an interval that was that had a limit of 0, and so this interval became smaller and smaller, and it became infinitely small. And when it was actually infinitely small, and as that limit went to 0, we decided, okay, so there's our slope. So that's what we did early in this course. One of the things that we missed from the 6.4 that we're skipping over is Riemann sum ends up being, well, if I take this as an area, and I take this area under the curve, this shaded A of x, and I should say that so we're going to start from point A on the left to some point B on the right. And if I want to figure out what the area is, well, it ends up being hard because it's a curve. But if I take that kind of trapezoid area, and then if I take this next one, and I'll have this trapezoidal area, and if then I have this one and I have this trapezoidal area, if I add all of those areas up, that should be pretty close to what A of x ends up being. How could I make it even closer? Well, if I take smaller and smaller pieces and more of them, then we should get really quite close to the actual area of that curve. And in fact, if I take these slices of that curve that are infinitely thin, and I take infinitely many of them, that should end up being equal to that whole area under the curve. That is what 6.4 was about with Riemann sums, is what we missed from there. So all of that said, what 6.5 starts off with, it starts with this discussion about, all right, so we do have this line of y is equal to f of x, and we consider the left side is x is equal to a, and the right side is this x is equal to b. And we have this area that is bound between the x-axis and this curve that's above it, and is bound on the right side by the line x equals b, and on the left side by the line x equals a. We're going to call that a function a of x. And a of x is going to be defined for an interval from a to x. And it'll be our area. So it's a function, and it's dependent on this interval from a to x, that it is the area that's under this curve and bound by these things. If we talk about the area, or a of little a, that ends up being equal to 0. Well, it's equal to 0 because it's the area bounded by a on the left and then a on the right, which ends up being this infinitely thin area. And in fact, it's so infinitely thin, that area ends up being equal to 0. So we could argue the width of the area bounded by A on the left and um, if this is A of X, that ends up being our right bound of it. So therefore, my right bound is also A. So A on the right. Its area, 0. Is really, that's all that we're getting at with this diagram. In the next example, okay, so this starts to maybe look a little closer about what this means to have this area. So we have this function f of x is equal to 3x plus 2. It's just this linear. We have a trapezoid, which ends up being the area under that curve and then down to the x-axis. We have an interval that goes from 1 to 1 on the left side to x on the right side. And so we have this shape, which actually ends up being a trapezoid. Now, I'm not sure if you remember much about trapezoids from junior high, but the trapezoid has 2 bases. There's going to be base 1 and base 2. And the area of this thing is also dependent on the height between those 2 bases. And so it ends up being, our formula for this ends up being height times, well, b1 plus b2 over 2. That works because that gives us the average length of base, adding them up and dividing by 2. And if we take the average length of that base and multiply it by the height, that ends up giving us our area of the trapezoid. That said, we now have this trapezoid that kind of looks like it's on its side compared to what I just drew. We have the bases of it are here and here. So there's your base 1 and your base 2. The height of it ends up being this. So if we want the area of this thing, then it ends up being 1/2 times height. And the height of that horizontal distance between those 2 parallel bases ends up being x minus 1. If now we're going to add up our 2 base lengths, this one over here on the right, that ends up being f of x. And this one over here on the left ends up being f at 1. So we're adding those together. And that should return us the area of this thing. Okay, so if we follow this through a bit, this ends up being 1/2 x minus 1 times f of x, which is 3x plus 2. That's our function. Plus f at 1. And f at 1 is when we plug 1 in for x, this ends up being 5. All of this together, 1/2 x minus 1, 3x, 7. We'll be able to simplify this out. This ends up being 1/2 3x squared, 4x minus 7. I distribute 1/2. This is 3/2 x squared plus 2x minus 7/2. So here is a function. Here's a formula for the area going from 1 to x. And so no matter what x ends up being, we can change this. But a couple of things to notice about this. A prime, so if we take our derivative of that area function that we just found, this ends up being 3/2 x times x squared, we take the derivative of that. This ends up being 3x plus 2 is our derivative. But f of x was also 3x plus 2. Therefore, the derivative of our area ends up being our function f of x. That is, the derivative of the area is equal to that curve. So therefore, capital A, which is our area, is capital F of x plus c. So our area ends up being the antiderivative. All right, which is really quite a profound thing. And it actually ends up being pretty powerful. There's a lot that we're going to be able to do with that. Okay, so in this next example, therefore, let's determine the area of this curve under this curve of f of x equal to 3x plus 2 and above the x-axis on this interval from 1 to 3. Well, so the area is equal to f of x plus, we take the antiderivative of 3x plus 2. Here it's 3, change it to x squared, adding 1 to the exponent, also by dividing, therefore, by 2. The plus 2 becomes plus 2x. And then we have plus c. What we did in the previous section about looking at initial conditions, when we looked at that acceleration and velocity and displacement function, is we take initial conditions, f at 1 is equal to 0. So what we were looking at earlier here, and saying the area from 1 to 1, well, that ends up being equal to 0. So therefore, 0 is equal to 3 halves x squared plus 2x plus c. And when x is 1, this ends up being an area of 0. So 0 is equal to 3 halves times 1 squared plus 2 times 1 plus c. We subtract 3 halves and 2 over to the other side, we get negative 7 halves is equal to c. So therefore, ax is equal to 3 halves x squared plus 2x 7 halves, which is what we had up above. So here is our function that finds the areas of the curve from 1 to x. So the area going from 1 to 3 is a3. So a3 would be 3 halves times 3 squared plus 2 times 3 minus 7 halves. And when we math that all out, that ends up being 27 halves. 6 minus 7 halves is 20 over 2 is 10 plus 6 is 16 altogether. All right. So now what happens if we look at some other curves? We have 2x squared plus 3. That looks like perhaps something like this. We want the area under this curve from 1 4. We're finding this area going from 1 to curve that's below this parabola. Right? So we start by taking a of x being your antiderivative of this function. Function is 2 times x squared. We add 1 to the exponent, divide by that. The plus 3 becomes plus 3x. And then, let's see, the area at 1, just the area of this that line there, the area at 1 is equal to 0. So therefore, 0 is equal to 2/3 times 1 cubed plus 3 times 1 plus c. C is equal to negative 11 over 3. All right. All of that put together, a of x is equal to 2/3 x cubed, 3x minus 11/3. And we're interested in finding a at 4. The area to the left at 4, so bounded from 1 to 4, and this ends up being 2/3 times 4 cubed plus 3 times 4 minus 11/3. We end up with 128 over 3 plus 12 minus 11 over 3 ends up being 117 36 over 3, 53/3 equal to 51. So just using this initial condition that a at 1 is equal to 0, and then evaluating a at 4, and this equal to 51. So we end up, now we want to come up with a process, and let's get rid of that idea of C. We can do this generally. We had done this in the last couple of questions by, okay, let's look at the area at that left bound and it's equal to 0, and so let's subtract that and figure out what C is, then we'll plug C back into our, if we did all of that in our formula, if we did all of that math kind of ahead of time, then what would that look like? Okay, so this is saying if we have this curve y is equal to f of x, then the area under this curve is a of x is equal to capital F of x plus this amount c. But if the area from a to a is just 0, therefore 0 is equal to capital F at a plus c. And if we solve that for c, therefore c is equal to negative f at a. So if we substitute that in for c, then a of x actually ends up being f at x, but instead of plus c, we have minus f at a. which ends up being our area bound on the left from A to on the right by X. And in general, we'll end up calling it the area of B is equal to F at B minus F at A. Is your area from A to B. So to determine your area under a curve, find your antiderivative of this function, evaluate from the right bound to the left bound. And we'll subtract those. What it looks like is F at B ends up being everything, the area of everything left of B is F of B. And everything to the left of A is F at A. And if I subtract those, if I take this whole area, and if I subtract this portion, well, then what we're left with is this. Ends up just being the area from A to B, which is called the fundamental theorem of calculus, which is what we're going to look into in section, we'll look into this in section 6.6. Thank you, and let me know if you have any questions.